In Chapter 10, we'll talk a little bit about the periodic table in a modern atomic theory. We'll start the chapter off by talking a little bit about electromagnetic radiation, which is a form of continuum. It's a form of energy that runs a continuum from radio waves to X-rays, and this includes visible light and microwaves as well. Since we're talking about waves, we should probably go over all the features of waves. So in this case, the first thing you want to talk about is the wavelength. What is the wavelength? The wavelength is from a peak in the wave to the same spot of a peak in the next wave. So it's the distance between consecutive peaks. So right here, that's one wavelength, or if you want to count from the bottom to the bottom, you can do that as well. But that's one wavelength, okay? The amplitude is how tall the waves go. And frequency is the number of times a wave passes through a certain point per second. So like if it goes to a second, that tells like if it goes 5 times through, then the frequency is 5 right there. Speed is how fast a wave moves through space. So different wavelengths of waves will actually end up giving you different colors. In the visible color range, visible light has color because red has a certain wavelength, yellow has a different wavelength, and then blue has a different wavelength. Now, obviously, there's different other wavelengths that you can't see that, like radio waves, you can't see those, and you can't see microwaves, and you can't see X-rays, and those because those wavelengths are not falling in the visible range colors that our eyes can detect. And amplitudes, on the other hand, if you have a small amplitude, a short wave, like that's not tall, this would result in something like dim, or if it's a sound, it would be very soft. And then if it's a higher amplitude, it will be a brighter color, darker, and then, or if it's a sound, you would hear a louder sound. So here's the electromagnetic spectrum we were talking about. We have it on frequency scale, energy, and wavelength. Okay, so one thing you gotta remember is shorter wavelengths is the same as high frequency, and that will be high energy. So you see here, if you're high energy here, your wavelength is your frequency is really big, but your wavelength is really small. Okay, so I like to tell everyone frequency and energy is the same. Wavelength is going to be the opposite. Okay, so you see how the colors that we can see, it falls in such a small tiny range right there in the visible light range. All the other guys here we cannot see with our eyes. So we have radio waves, the lowest energy, so that means it's the lowest frequency, but the biggest wavelength. Okay, the wavelength is so big you'd have to run a few seconds or minutes to cover one wavelength. That's how big it is. And then you have microwave. Their frequency is getting bigger, and the wavelength will get smaller. And then you have infrared, and then red in the visible light. And then, so you got red, and then the color changes, and then you got purple, which is violet on the other end here. This is the highest energy of the visible light. This is the lowest energy of the visible light range. And you see how the lowest energy side has a bigger number in wavelength, and the highest energy has a smaller number in wavelength. That's because energy and wavelengths are opposite, and frequency energy is going to be the same trend. Okay, so infrared leads to red, and then violet here in the visible light will lead to ultraviolet UV rays here, and then after that we have X-ray and gamma rays. So gamma ray is even higher energy than X-ray here. Electromagnetic radiation has wavelength and particle properties. So the particle part, we want to describe the energy as packets of energy called photons. Radio wave has the lowest energy, this obviously is right here, low energy, and then gamma ray has the highest energy. High energy electromagnetic radiation can potentially damage biological molecules, and we can see that already, even with the UV rays from the sun that can damage our skin, and that causes damage in biological molecules too. Let's talk a little bit about the Bohr atom. So what's interesting is if you take an element and you either put high voltage on it or high temperature, you see that these elements emit, so they basically release a colored light. Okay, when they take this light and then pass it through a prism, and you can see it splits them up into colored lines. So like you see a pink line, a blue line. So whatever that light that comes out, you put it through a prism, you see individual lines here like that. So how do we explain that? These individual lines here indicate that the light has specific wavelengths or frequencies or energy packets. Okay, just specific ones. It's not continuous. It's individual lines right here. So each element possesses a characteristic and unique line spectrum. So this is the line spectrum here, where if you take hydrogen, there's a pattern, and then you take carbon, there's a different pattern. Like the bigger the atom, the more complicated the line it becomes, and the closer to when you get to uranium, all those lines are filled in almost the whole way, and there's going to be very few blank spots. So the blank spots here are the black space right there. Okay, how do we explain this? So Bohr gave a theory. He proposed this. Okay, we have since then proven this wrong, but this was what he proposed. So from his study of the line spectrum in hydrogen, so he studied hydrogen a lot. And this is why it broke down. After hydrogen, you get helium and all the more complicated atoms. His theory broke down. Okay, so it's been proven wrong basically. But he proposed this picture here where the nucleus is in the middle and the electrons are orbiting in fixed positions around the nucleus. These are possible electron orbits right there. So like there could be an electron here, either orbiting around this line, or maybe there's an electron orbiting here, electron orbiting here. It's just fixed in that line, the circular line around it. So these lines, so what do these lines mean? So right here, here's a proposed idea, and this still stands true. It's just that is the way the orbits are not exactly true anymore. So when you shine some energy like high temp or voltage or some sort of energy form onto the element absorbs the energy, and it absorbs the energy um, um, by taking the photon in. Okay, so when they take a photon in, the electrons get bumped up to higher energy levels. So like if you start from level ground state right here, and then you absorb a certain energy, maybe you absorb this much and you can go up here. Or if you absorb a lot of energy, you can go up at the next level. Okay, so once they absorb these energy, what happens is you see something coming out. So what we're seeing is the emission, not the absorption. We know we give them energy and then we see an emission. So the emission is basically once the thing that's excited, electrons excited, it will eventually relax back down to the ground state or a lower state than it was, and in the process release a packet of energy, a photon, that whatever the wavelength is, if it's in the visible light range, you can see the colors. Okay, if it's not, then obviously you can't see it, but in this case it was in a visible light range, so we saw a color. And then you took a look here. If the energy level is smaller, you get a red color. If there's a high energy level, a bigger one, you get a blue color, because blue color is higher energy, or purple is even higher than blue compared to the red. Red is the weakest color. Okay, so the color that you see coming out is because the electrons are relaxing back down to ground state and they emit a packet of energy, a photon, and the photon has a certain wavelength that you can see the colors. Okay, so that is how Bohr learned that you can quantize energy where you can count electron packets of photons. So basically, recap. Ground state is the lowest energy level, okay? And then each line corresponds to an emission or whatever color it is. It's whatever the wavelength of that photon that's coming out. And then the color of light depends on the gap. The smaller the gap, the lower energy, closer to red. if it's in a visible range. If it's high energy, it will be closer towards the purple color. If it's even higher, it goes in the UV range, you can't see it anymore. So it works really well until you go to multi-electron system, because hydrogen only has one electron. And this theory breaks down. Okay? So why did it break down? It's because our electrons are not just particles, it also has a wave-like property. Okay? So matter can be wave or particle at the same time. So it's not just like energy isn't just wave, isn't just photons or particles. In this case, it's both. Okay? So because it's both, for large objects, the wave property isn't really noticeable because their wavelengths are so small. Okay? But when you get smaller objects with really, really small mass, like an electron, the wave-like properties of those guys become a lot more important. It makes a big difference then. So basically, things like electrons here, the wave-like character becomes prominent and it starts taking an effect. So what happens here is we have to combine both the wave-like properties and the particle nature, wave and particle, combine them together so you can have an equation describing these electrons. So it's not just a particle. Electron isn't just a thing, it also behaves as a wave. So this theory is called the quantum mechanics, and it helps us calculate the probability of finding an electron in 3D space. So just an area, a location space, okay? So it's just where would the electron be? It's no longer in just a fixed orbit like Bohr was saying, like fixed orbit. We gotta find out where the electron is. And it turns out it's like a density map. You can find a probability of the electron in that one area, and we kind of map it out that way. Okay? So what we end up mapping out is the electron probability, and these orbits that Bohr was talking about is now replaced by orbitals. So orbitals are the locations where there's a high probability of finding an electron in there. So the funny thing about this quantum mechanics is the wave and particle nature is you either know one part or the other part. You don't really know the whole picture. You can't see the whole picture, but so we can only find a probability of it. Okay, so in this picture here for hydrogen atom, they start mapping out like, okay, well, it could be here, it could be here, it could be here, and then it ends up the probability looks like a little sphere. That's an orbital for a hydrogen atom with just one electron. So there's one electron, it could be here, just anywhere in this map right here where there's a dot, electron could be there. Okay, so that's an orbital right there. So instead of an orbit where it's fixed circles, it's just actually in 3D space. Like this is the area it's most likely to be in. This is a sphere space, 3D shape. Okay. So in this case here, when we start talking about quantum mechanics, we have to start being able to count. Like, we have both nature. We have particle nature and we have wave nature. So in this case here, we want to talk about how we predict discrete quantized principal energy levels. So we have discrete energy levels, like obviously you saw those colors come out, the emission from the atoms, there's individual lines here, right? So we had to combine the particle nature with the wave nature to come up with a theory. And now, instead of just the energy levels according to the orbits, we know where the orbitals are, and then these are the energy levels. So there's a lowest energy level where I call n equals to 1. You start at n equals to 1. That's the lowest energy level. Okay? And then the next energy level, you start at n equals to 2. And then you go up higher, n equals to 3, 4, and then 5. Now, what you want to notice is as you go up higher levels, the gap gets smaller and smaller with the higher level you go. And eventually, if you go to infinity, the line is continuous like a band. Then that's when it becomes a complete wave like a classical physics. And this down here, when it's really, really small energy levels, it becomes the quantum mechanics instead of the classic physics. Okay? But we don't really need to worry too much about it. We just need to know there's energy levels. Level 1, level 2, level 3, level 4. And these here tell us a certain amount of energies in there. And there's going to be orbitals in each level. Different orbitals. There's going to be orbitals in level 1, orbitals in level 2, orbitals in level 3, level 4. We'll talk a little bit more about that. Okay? But the higher the n, the higher the energy. These are low and lowest energy, and it just keeps going higher. So let's talk about the first level, okay? N equals to 1. In the first level, we have 1s orbital, okay? This is where an electron is probably going to be at, in this sphere right here. So level 1 has one sphere, and the spherical ones, we call it an s orbital. Now, based on that, we also want to learn about electrons inside the orbital. So we were saying in the orbital, there's probably an electron. When we're talking about hydrogen, it's just one electron. What if we got multiple electrons? Where do they go? How many electrons can fit in an orbital? So what it says here is an orbital can only hold 2 electrons. And these electrons must be opposite spins. That means one is going up, one is going down. Like we represent it with arrows, okay? So when you draw electrons, you can always put 2 electrons inside one orbital based on that map there. So like hydrogen has that little sphere, and we know hydrogen only has that one electron inside the sphere. And but helium is going to have 2, so there's going to be 2 of them in there. So you represent the first one as going up, the second one is going down. That was the first level. So second level, we have n equals to 2, slightly higher energy now, okay? Slightly higher energy, but now instead of just the sphere, we have multiple options here. So we have the 1s orbital that was for hydrogen earlier. Now we have 2s, okay? 2s is just a bigger version of 1s. So it's just bigger. So if we had a picture here, let me draw it out. So if 1s was a little small sphere, 2s will just be a bigger sphere. So just like bigger. Okay, and then if you imagine 3s will be even bigger. Okay, so that's the only difference. So they're bigger and higher energy. That's what it says right there. Larger and higher energy. Now, that's the spherical ones. And then you end up seeing, oh, by the way, in level 2, there's another type of shape of orbitals after that. There's dumbbell looking ones. So there's a dumbbell this way, the orange color, the purple color dumbbell, and the blue color dumbbell. There's 3 different dumbbells possible. So you see here level 2 is unique because you start off with a sphere, and then you have 3 different dumbbell shaped orbitals. Okay, so I guess we should write down, yeah, so that's the 2s, and these are going to be 2p in this case. So because of that, level 2 will have 4 different kinds of orbitals, and that means they'll have 8 electrons. Each p orbital still has 2, so every orbital can only hold 2. Okay, let's talk about level 3. So earlier, level 1 had only 1s, a sphere. Level 2 had the 2s, a bigger sphere, and 2p's. And there's 3 kinds of 2p's, right? Also, level 3 gets even more complicated. Level 3, you'll have s orbital 3, so it's a bigger one than 2s. And you have a 3p set, same thing like 2p, but bigger. And then the new ones, you have 3d orbitals. So let's take a look at what they look like. Okay, so d orbitals, it just looks like 2 dumbbells stuck together, like just different on different axes, like in 3D range. You see how? And then this one here, I like to say, oh look, there's so many dumbbells. So after you go to the gym, you work hard, you can have a donut. There's a donut ring around this dumbbell. So these are double dumbbells. There's 4 of those, and then the last one is a donut ring around the dumbbell. Okay, so those are the shapes you want to try to remember This is the shape of 3Ds. Now, imagine if you had a 4D, then 4D would be even bigger, but same shapes, just bigger. Okay, so the higher the level, the bigger it is. So let's do a little recap here. We had the orbitals, we had 3s, which was a big sphere, okay? And then we talked about the 3p, we got 3 dumbbells, so bigger dumbbells than earlier. So I'm drawing the dumbbells out separately, but there's 3 of those. And then you got your d orbitals. So this is 3D, 3D, 3D. They're all 3Ds right there. 1, 2, 3, 4, 5. So all together in level 3, you got 1 orbital, 2 orbital, 3, 4 orbitals. And then there's 5 here. So 4 plus 5 altogether, there's 9 orbitals. So you really could hold 18 electrons in the third level. Okay? So let's go to the next slide. So each level gives you new orbitals, right? So let's do a recap here. Level 1, we had 1s and it looked like a little sphere. Maybe we can draw the sphere out. This is a small little sphere. And then level 2, the sphere got bigger. Okay, level 3, the sphere gets even bigger. And then can you imagine level 4s? The sphere gets even bigger. Okay, so now remember 2p, we were drawing a p orbital. So level 1 doesn't have p's, okay? Level 2 has p's, and this is what it looks like. So we got 3 dumbbells. So a dumbbell here, a dumbbell here, and then a dumbbell there. Maybe I'm running out of space, but those are my dumbbells. And guess what the 3p dumbbells look like? They're just the same thing, but bigger, okay? So we're gonna eventually run out of space, but maybe I'll draw the 3p and then you can just imagine the 4p being even bigger right here. So a little bigger. Okay? And then 4p super big, so let's draw it even bigger. Okay? And then what about the D's? Remember the D, they look kind of funny. The D shape, we had a bunch of dumbbells, like double dumbbells like that, right? And all different like orientation. And then the last one, remember, it looked like a dumbbell with a donut ring around it. Okay? And the difference is for 4, it will just be bigger. And then for F orbitals, the next level, level 4, has F orbital. F orbitals like crazy. So if you ever see pictures of F orbital, you'll see that if they're not dumbbells or double dumbbells, a dumbbell with a donor ring or a sphere, those are going to be F orbitals. Okay, so that way you don't have to memorize because there's so many different ones. So here's a question for us. What is the maximum number of electrons in the 4D sublevel? So they're talking about 4D right here. Maximum electrons, that means every orbital is completely filled. In each one, we have 1, 2, 3, 4, 5, correct? So if they're asking for just 4D, there's 5 of them. 5 times 2 will give us 10 orbitals because each orbital can hold a maximum of 2 electrons. So the answer will be 10 there. So what about the next question? It says, what is the maximum number of electrons that can occupy the n equals 3 level? So that means the entire level of 3, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 orbitals, and each one can hold 2. That means we can hold a total of 18 electrons right there. So let's talk about atomic structure of the first 18 elements. Obviously hydrogen has only 1 electron, so the 1 electron is going to be in a 1s orbital. Okay, now when you start getting more electrons in the system, that's when the Bohr theory failed, and that's why we have this quantum mechanics with more orbitals to hold where the electrons go. Okay, so let's see how we can fill it up. Each orbital fills 2 electrons, right? And then you start with the lowest energy first, before you go to P, before you go to D, before you go to F. So you start from the low energy before you go to the high energy. And you always go within the N level. Like you fill in level 1, Like level 1, you fill in 1s. And then you go to level 2, fill in 2s first, and then you fill in 2p's. And then you go to level 3, 3s, and then 3p, and then 3d. You go in order, basically. We'll have examples. And then each orbital in a sublevel must contain an electron before another electron can add to any other orbital. So this one means when we fill it up, it feels kind of funny. Like say we have like 3 sets here. Like, you know how p orbital has 3 of them, right? So remember we point up like this, and we know we can have a total of 6 6 electrons in the orbital here, because these are, like, say, let's pretend this is 2p. Okay, so the first electron goes here, the second electron goes there, the third electron goes there, the fourth comes here, fifth, and then sixth. So that's what they're saying. You must fill in an electron, like, in each one, so that you go point up, up, up before you come back down. So how do we depict this? A lot of times we use pictures. That works, but there's going to be better ways because we can't be drawing pictures all the time, right? So in this picture here, this is what fluorine atom looks like. You have 9 protons, because fluorine is the 9th thing, and then a neutron is just depending on how many neutrons. That doesn't really matter. You can tell different neutrons here. If fluorine has something that has 11 neutrons, then it will be an isotope right there. But you have sodium here, 11 protons, and then magnesium, you have 12 protons. In this case, this one has 12 neutrons, 10 neutrons. That part doesn't matter too much, but because it has 9 protons, we know we have 9 electrons. Because it has 11 protons, we know we have 11 electrons. Because we know we have 12 protons, we have 12 electrons, just because it's neutral. Neutral means there's no charge. The electrons and the protons must balance out. Okay? So the next thing is we use electron configuration. This is when we start talking about the level 1s, level 2s, level 3s, that kind of stuff. Okay? So the first number, 1 or 2 or 3 or 4, that's the principal energy number, principal quantum number, the first number. It tells you what level it is. And then the S, P, D, F, that tells you what type of orbital, right? The shape it takes. And then how many electrons are in that sublevel, that type of orbital there. In this case, there's. So going back to the other one, it was 2p6 right there. That means there were 6 electrons in the p orbitals of level 2. Okay, so another third way to represent our diagram is we use orbital diagrams. Instead of writing 1s2, we can actually draw a box representing 1s and then fill it up with 2 electrons. So you'll see that we typically don't use the diagram to draw it out. We either use the orbital diagram or we use electron configuration. So that's an orbital diagram. Hydrogen has 1 electron because it has 1 proton. If it's neutral, then it will have 1 electron. And then we have electron configuration of 1s1. That means it's level 1, obviously, and we have the first electron in level 1. Okay, let's take a look at helium. Helium has 1 extra electron, so we're still on the first level. So it'll be 1s2 because there's 2 electrons in helium. And then if you go to lithium, lithium has 3 protons, so we'll have 3 electrons. So it'll be 1s2, and the third electron is in level 2, level 2s. So that's the orbital diagram for that one. 1s2, 2s1 is the electron configuration. Beryllium is the next in line. So that means it has 4 protons. That means for the atom, you'll have 4 electrons. So if we fill in the orbital, both of them will be 1s2 and 2s2. Both of them will be filled. And if you write the electron configuration as 1s2, 2s2, just like that. If you keep going, so next we have boron in the list. We have boron with 5 electrons because it's got 5 protons. So it'll be 1s2, 2s2, 2p1 right there. And then if it have carbon, it's 6 protons to 6 electrons, 1s2, 2s2, 2p2. And if you notice, we go spin up, without going to spin up and down at the same time. We always have to fill in one in each orbital before we come back down. Okay? Go to the next in line, nitrogen. Nitrogen is 1s2, 2s2, 2p3. So one extra electron after carbon. So you have 1, 2, 3, all of them spin up. Now oxygen finally is when you start coming to spin down, because oxygen is one extra from nitrogen. It's 1s2, 2s2, 2p4 in this case. So you go spin up, 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 and then down. Okay? Fluorine is the next one in line. So fluorine is going to be one more extra electron. So 2p5. So you go 1s2, 2s2, 2p5, 1, 2, 3, 4, 5. So the fourth and fifth one is spin down. And neon, remember, everybody likes to be like the noble gas neon, right? Because it's completely full, perfect electron configuration. You see that? 1s2, 2s2, 2p6. It's perfect, it's super stable, it's completely filled, and it's all spin up, spin down all the way because it's all full. So here's the table of our orbitals, the way they fill it up. We just went through all of them together earlier, but here's a recap of it. So if we go beyond neon, we have sodium. We start getting into level 3 now. So we just fill up what was there before, and we start with level 3s1. So and you can see that it just keeps adding. So this is level 3 here. And then if you take a look, this is sodium, we got 3. And then magnesium, we got this atomic number is number of protons, so we got 12. So that's why we got 12 electrons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so it just keeps going on. And you see here, once you fill up the 3s, you start going to 3p. And then you start going to 3p2, and then 3p3. And then you start coming spin back down. 3p4, 3p5, 3p6. And see, we hit another noble gas right there. Okay, so we got level 1s, level 2s, level 2p, 3s, and 3p, and then it just keeps going, but this is until the 18th one. So here are the electron configurations. So for example, for argon, it'll be 1s2, 2s2, 2p6, 3s2, and 3p6. Okay, so these are how you write electron configurations, and it tells us where the orbitals are going to be, and each orbital obviously has a different size, right? The bigger it is, the probability of finding an electron is in a bigger area. So here's our periodic table. I wanted to point out how you can see where the 1s, where the 2s, and all that stuff is. If you notice, you start with 1s, right? So this guy here was 1s right here, was 1s1. Okay? And then you go to helium, you get 1s2, correct? So it was still level 1 because that's period 1. Okay? You go to the second period, this guy is here, now you have level 2s. So this is 2s1, this is 2s2. Okay? And what's cool is, what's after 2s? You notice you take a break, and then you go to this right here. So there's actually 6 of them. What does that look like? That looks like the p's. So this is 2p orbitals here. So this is the 2p's, where boron is going to be 1s2, 2s2, 2p1, right? So the 1s2, so everybody below that. So this is 1s1, this is 1s2, and then lithium is 1s2, 2s1, and then beryllium is 1s2, 2s2. I'm just writing the outside here, right? Let me go ahead and add the inside levels in too. So this is 1s2, 2s1, 1s2, 2s2, right? So we kept going 1s2, 2s2, 2p1, and then this guy carbon here would be 1s2, 2s2, 2p2. Okay, so I'm going to start skipping writing the initial parts just because I'm going to run out of space. So I'm just going to read off the last one every time. So if this is 2p1, this will be 2p2, this will be 2p3, this will be 2p4, 2p5, 2p6. You guys see that? All right, we had an example on the previous slides anyway. But then what's cool is after you finish your 2p's, you start going to the next level, and guess what? This is level 3s. And then this is level 3p. So it follows the periodic table. Okay? So that's what the cool part is. So remember, this area here, we start period 3, so it's 3s. And this area here, period 3, so that is 3p's right here. And there's 6 of them because you can hold 6 electrons. There's 6 different ones. And then once you go down to the next level, right here, you start getting into level 4 here. So I'm going to keep showing you. This is level 4s right here. Okay, the first two is always, so this is 4s. And then what's cool here, this guy here, these are the 4Ds. I mean, not 4Ds, 3Ds, okay? So let's erase that 4 off right there. Okay, and then, so D is super weird, 3D is super weird right there, but let's keep going. I'm going to show you. This is level right here, level 4P, okay? And then you have level 5S, and then this will be level 4D, and then this will be level 5P, okay? So one weird thing is when it comes to the transition metal area, we're a little bit behind, okay? It falls a little bit behind, so we have 3D here. Because remember we learned that level 3 we had 3S, 3P, and 3D, but the 3D falls after the S, okay? The reason is because everybody's slightly different energy. So let me give you an illustration here. If you had this picture here, where the energy levels, remember how first energy level, and then there's the second energy level, right? And then the third one is closer, and the fourth one is even closer, remember that? So this is N1, N2, N3, and this is N4, okay? So when we start doing that, we knew that level 1 had 1s, and level 2 had 2s and 2p, so 1s would be right here. So we'll just draw like, okay, maybe level 1 right here. And then level 2s will be right here. And then level 2p will be right a little higher. 1, 2, 3. Like that. Because there's 3 types of p orbitals, so 6 electrons. And then you go to level 3, you're like, okay, well, my 3 is here, 3s. And then I have 3p, right? Oh, my 3p gotta draw it a little bit higher than that. Let's erase that small spot. Okay. And then we go a little higher. You start going this way. You see how it's getting so close? But that's 3p, so this was the S, and this is 2p here, and this is 3p here, right? So those S's were there, so 1s, 2s, 2p. Okay, and then you see how D is even higher. D is like right there. 1, 2, 3, 4, 5. This is 3D. And you're like, oops, we just crossed over level 4. And level 4 is right here, 4s. So that's what happened there. It just crossed over because it was getting higher and higher energy, and because the gap was getting closer, it crossed over to the next line, and that's why the D comes after here. Okay, so this is 4s, and then 4p, and this is 3D, and then 5s, 4D, and then 5p, like that. And then if you keep going, numbers just keep getting bigger. So this will be 6s here, 7s here, and this is 5D and 6D right there, okay? And you see how there's a little gap here? These are where my F's are, okay? And F's are 2 behind. So these is 1 behind, right? F level will be 2 behind the original right here. So this was 6, let me write it down. This was level 6S, level 7S, okay? And then this is level 5D. This is level 6D, okay? And then these guys here, 58, you see how there's 57 and it goes to 72 right here? This is 58 here. So these guys here are going to be your level right here. Let me put a different color. So this whole here thing here, this is level F, the weird orbitals ones. This is level 4F. And this is level, the next level, 5F. But we're not going to really do anything a lot with these weird stuff. We barely go into the D's usually anyway. Okay? But that's there. Oh, I forgot the last one. Let's label this one too. This one will be level 6P. Okay? So based on this periodic table, it tells us what levels we are and what kind of orbitals we have. Okay? So this will be very good. Maybe it will be a good idea for you to print out a periodic table and label these along so you can follow and you remember how to read the electron configurations. We'll have a lot more practice coming up. So valence electrons is defined as electrons that are at the highest energy level, the outside. So if you're level 1 and level 2 is the outside, that's my valence right there. So I got 2s2, 2p6. That means I have 6 in my valence electron. That would be oxygen, okay? Oxygen has 6 valence electrons. Total of them is actually 8, but only 6 of them are on the outside. And that's why you find oxygen in group 6. So the valence electron tells you what group it's going to be in because we group them according to valence electrons. Why? Because depending on the number of valence electrons, they have unique properties depending on that. So it says here, see, 1A to 7A in a periodic table. So we'll take a look, okay? And it gives you the valence electron. So you see 1A, 2A. So 1 valence electron, 2 valence electron, 3 valence electron, 4, 5, 6 valence electrons, 7 valence electron, 8 valence electrons. Those are your groups, and it tells you the valence electrons. Okay? How many valence electrons does phosphorus contain? Phosphorus is right here. It's number 15. What group is it under? 5. So it's valence electrons that will be 5. And if you wanted to write the electron configuration for P, it looks like this. P is right here. Okay? So we can count 1s2, and then we got 2s2. We got everybody in 2p6, 3s2, and 3p3. So the full electron configuration for phosphorus is 1s2, 2s2, 2p6, 3s2, and 3p3. And if we were to draw them, I'm just going to draw the last one now, the 3p here, right? It'll be spin up, spin up, spin up. Okay? So it says how many valence electrons? The valence electrons only want you to count those in the outside level. So that would give us 5 as our answer. So our answer would be A. I also showed you the valence electron configurations. So make sure you practice, pick an element and write the electron configuration and maybe draw out the last part. And also you can pick out what group it is to tell how many valence electrons in it. You can do it with any element in the periodic table. So which element could have the following electron configuration? It's 1s2, 2s2, 2p6, 3s2, 3p6. So let's go ahead and follow it. 1s2, 2s2, 2p6. So neon would be 1s2, 2s2, 2p6. It will stop right there. But then we're not there. We got some more electrons in there. So we got 3s2. Okay, magnesium would have stopped at 1s2, 2s2, 2p6, 3s2, right? That's 12 right there. But we actually have more. How many electrons do we have in total? We have another 6 more. So 3p6, 3p1, 2, 3, 4, 5, 6. So it's right here. It's argon. So argon is our answer because argon would fit the description of that electron configuration right there. So let's practice. What would be the electron configuration for Cl? So Cl is number 17, okay? So for Cl, is number 17, and I can see it's at 1 less than argon. So we end at 3p5. Okay, so you can check and count with me, but it's 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so that's how we would end up there. Because it's 1 right before argon. We counted all the way to argon just now. And then let's look at calcium. Calcium is actually past argon. It's 2 past argon. So you can write everybody that's in argon. So here's where we start. I can show you the short form. So calcium, you can write down all these guys above it, or if you're trying to do a shortcut, you say, oh, whatever argon was. And then we say calcium has 2 more electrons because it's 19 and 20. So it'll be 4s2. Okay? And then sulfur, let's do sulfur. We take a look at sulfur. Sulfur is right here, is number 16 here. And it's before chlorine and before argon. So chlorine was 3p5, so sulfur must be 3p4. So I'm just going to go ahead and write down. Another way to write a short form is instead of writing all the way up to neon, which is 1s2, 2s2, 2p6, right? See, this here is neon. So if I wanted to write something for sulfur, which is after neon, you can say, well, how about I just write neon, everybody that was in neon, and then plus 3s2 and 3p4. Okay, so that's how you do a short form. So if you have Cl here, technically we could have written the short form of neon, and then 3s2, 3p5. It's the same thing, okay? So how are the atoms in the periodic table arranged? Well, it depends on the number of protons, and we try to group them by the type of valence electrons they have, because the same valence electron will fall in the same group. And they organize them based on increasing atomic mass, which is increasing number of protons, okay? So like we said earlier, we have columns. These are groups or families, but we usually call them groups. This is group 1, alkaline metals. Group 2, alkaline earth metals. And then we have group 8, noble gases. Group 7, we have halogen. And then group 6, group 5, group 4, group 3. Remember, the groups here tell you how many valence electrons they have, okay? Groups are similar in trends. They have trends because they're similar because they have the same valence electrons, so they tend to behave the same. Now, when you go across here, this is period 1, and then period 2, period 3, period 4, period 5, period 6, period 7. It just keeps going, okay? And obviously, we arrange them in order of increasing atoms. Atomic mass number, so we have increasing protons right there. So we talked about periods as the going across. The period number is actually going to be related to the n. Remember the energy level? So if it's period 1, we'll have level 1s. Period 2 will have level 2s. Period 3, level 3s, that kind of stuff. But remember the d is a little off, 1 off. And then f is going to be 2 off, okay? And then we have the group numbers. Obviously, groups are based on similar things, similar elements, because they're the same valence electrons, okay? And then whenever you have the A groups here, these are the main group table, and B groups are in transition element. We mainly focus on the A groups. I don't even talk about the B groups very much. So right here, these are my B groups that we talked about. And so this is, the A group is the main periodic table. But we still talk about transition metals. I mean, we use it. It's just that we don't always talk about the B groups. We just call the whole thing transition metals. Okay? So alkaline metal, alkaline earth metal, noble gas, halogens, the same stuff we talked about earlier. Just a recap. Magnesium is a group of which group of elements, if it's a member of which group of elements. So magnesium is right here. Okay, group 2. So it's alkaline earth metals. This is group 1, this is group 8, this is group 7. So just like what we were mentioning earlier, elements in a group have the same valence electron, same number of valence electrons, so they behave kind of similar. So they're in a group, in a family, and they have their own names. Okay, so this is where we talk about the short form. Sodium is neon and 3s1. Instead of writing everybody that was a neon, just put neon in there. So instead of the long form, it would have been 1s2, 2s2, 2p6, and then 3s1. You replace this whole term with just neon. Okay, so that was the short form notation. So we're going to talk about the electron filling. We mentioned this earlier about how we filled 3D before 4s. Based on the periodic table, we could see that anyway, that the level 4s came and then 3D started appearing. It's because 3D was higher energy and it crossed over to the 4s level. Okay, so we can see potassium and calcium end up in level 4s1 and 4s2. This is in group 1, that's in group 2. And then you have your transition elements, okay, in the 3D subshell. And once the 3D is filled, we start filling the 4p. So we did mention that earlier. So here's a prettier version of the orbitals that we drew out earlier on the periodic table. It's 1s, 2s, 3s, 4s, 5s, 6s, 7s, right? And then you see how there's 2p, same as the main group all have the same levels. 2p, 3p, 4p, 5p, 6p, 7p is the same as the S, the same as the N level, but then the D starts going off like it's slow, one smaller, 3D, 4D, 5D, 6D. And then remember the F, we said it was 2 smaller because it goes right here. So it's 6S, 5D, and then 4F, and then they go to 6P, okay? And then same thing here, 7S, 6D, 5F, and then go back to 7P. So here's the question. The electron configuration AR, argon, 4s1 is the ground state electron configuration of who? So AR 4s1, this is AR, argon right here, plus 4s1, which would give us potassium. Our answer is A right there. Can you guys try to do phosphorus, fluoride, and sodium? We can do the short form notation, okay? So let's go ahead and work on that. What is phosphorus going to be? Phosphorus is number 15. So it will be before argon but after neon, right? So, and I can see that if you count the level, neon was level 2. P is going to be in level 3 right here. So I can write down the answer as everybody in neon, and then plus level 3s2, and P was the third one, so 3p3. Okay, and if you do fluorine, fluorine is before neon, so we can't really do a short form. We'll have to write everybody there. I guess you could do helium, but it's really not worth it. It's 1s2, 2s2, and then you see fluorine is number 9, so it's 2p5, okay? And then we have pf, and then Na, sodium, is number 11. It's right after neon, so we'll say neon plus 3s1. Those will all be the configurations. So here's the question. Who has the electron configuration and ground state for neon plus 3s2 and 3p1? So neon plus 3s2, 3p1. So if it stopped at 3s2, it would have been magnesium, but because they went another one, 3p1, the answer is aluminum right there. And you guys could take your time and try to do sodium, argon, and sulfur too. It's good to practice. All right, so in this case, we have groups. Remember we talked about it? The group number, they show similar properties, okay? Because they have the same valence electron. So here's a periodic chart with all the valence electrons in there just to show you. And you see how they only did the D's. They left out the F orbital side. With F would have looked even funnier. But you see how D is always one smaller than the S, okay? And then if you take a look, group number equals to number of valence. Yeah, this will apply if right here. If you have group 7, you have 7 valence. You have group 8, you'll have 8 in valence. Obviously, this one's unique because it's noble gas. Hydrogen and helium tend to just kind of stick out of place. But that's it for this chapter.